we are back. It will be Halliday, Resnick, and Walker, Chapter 29, Problem 10. So this is the 9th edition. Okay, so this problem here is it's a good one because you can put together a lot of concepts that you learned during Chapter 29. So this is what we have here. A wire forms a certain circle of radius r equals to 9.26 centimeters and in two straight segments, each of length L 13.1 centimeters, both in both sides here. Okay, the wire will carry a current of I 34.8 milliamperes. So my radius here, my radius will be 9.26 centimeters. So this we can already rewrite as 0.0926, okay, because it's going to be really better for us meters. And L here, the length of every single one segment, every segment here, it will be 13.1 centimeters. That means our length will be 0.131 meters, and our current will be 34.8 milliamperes, or if you prefer, the current will be 34.8 times 10 minus 3 amperes. Okay, and what are the questions here? What are the magnitude and direction into or out of the page of the net magnet field at the semicircle center of curve C? So if, guys, when you look to this picture here, uh, always we need to look for symmetry. Always, every time in electromagnetism, you need to look, to be honest, in all physics, but specifically these problems here, you need to look for symmetry. So take a look here, guys. What we have is we have section A, we have section B, and we have section C here. Well, if you remember, the, the formula that we need to use here, the best one to use here, it's our good friend Biot-Savart. So our good friend Biot-Savart, uh, the way that we can write this formula, it will be or dB, right, equals to mu0 divided by 4 pi, and I ds cross product with r hat. We will detail, we will, I will specify what is r hat in a few minutes, few seconds. So, and the distance r2. Well, when we look to this formula here, we start to think like, okay, so I know that this is the magnet field from a specific length, section of wire carrying a current I, a current I, and this is going to be the distance, the R going to be the distance from the point that I want to calculate this magnet field. So let's apply Biot-Savart for every single section here. Well, who is this formula? How I can apply this formula for section A and C? Because to be honest, it will be the same for sections A, section A, and C. Okay, let's take a look here. For section A and C, well, we can take a look closely who gonna be this guy here. So r hat is the direction of the the distance, the vector distance from the point that you are calculating to the point where is your reference. I mean, where do you want to calculate the magnetic field. So for this segment here, ds and r, ds, it's going to be this small segment here. So this guy will be our ds vector, and the r hat is going to the same direction here. So r hat will be into the same direction here. So because of that, as you know, this guy here will be I, ds, r, or simple like you can, because to be honest, this vector here, r hat, it's only the model of this guy will be equals to 0. So this is r, so the model of this guy gonna be equals to 1. Sorry. So what you have here, it will be okay, and the sine with the angle between these two guys here. So the angle here, theta, will be equals to 0. And because of that, this guy here will be 0 as well. So for the section A and section C, the whole Biot-Savart here is equals to 0. So it's not producing any field at point C. Okay? But let's try now check what it will be when we start to calculate the same Biot-Savart for section B, because now the game will change. Because I will give you just a heads up here. Take a look. We have our semicircle and we have our point C here. We have our R, the radius, right? And if we start to measure, that means if I have my ds right here, guys, if you agree, the ds will be every single small infinitesimal part here. Okay, so this one will be ds. So every single ds with the cross product with r hat, we're going to have 90 degrees here. Well, the 9 degrees will promote sine of 9 degrees, going to be equals to 1. So ids cross product with r, it will be ids. So for now, for my section B, the section B now, section B, what we will have, it will be the infinitesimal magnet field here, my constants, going to be 4 pi, and here will be I ds, and the distance from the wire to the point where I want to calculate my magnet field. Well, we reduce a little bit the Biot-Savart equation, but we still have to deal with, well, basically just ds, right? Because these guys here are constant. They're constant. The current is a static, is a current 34.8 milliamperes. So it's just a scalar. It's just a number. The radius here, so r is going to be equals to the radius from the point. So we need to deal with this ds here. Now, who is ds? Who is this guy? Well, guys, the thing is, when we have a segment of a curve, okay, segment of a curve, and we have r, we have the born of an angle, and this guy here, let's say that's going to be phi, and this is a small segment, okay, s. And we will start to figure out that the sine of phi, it will be what, guys? S over r. Agree? The sine of this guy, it will be s, because if we start to go really small, this guy will be I mean, it's not be a curve anymore. It's going to be really a line here, straight line. So sine of phi, it's going to be S over R. But when my phi start to be really small, my sine of phi is, sorry, my sine of phi, oh, let me read out this guy here. My sine of phi, it will be really approximate to phi when this guy starts to be really small. And that means phi, it will be equals to S over R. Well, S will be R times the angle. Well, but I need ds, so I can only derivate here. The s, the r will be the same, and here will be the phi. So ds, it's r d phi. And to be honest, guys, this is what we need, because we need to integrate over something. We need to integrate over something. So what we're going to do now, it's going to be, okay, so I will integrate both parts here. So it's going to be integral of dB equals to integral of mu0, and 4 pi, and times I. Now, this will not be ds. It will not be ds. Now, I will write down here as r d phi, right? And over r squared, because now I will plug it in here, the radius, into this part here, the r. So we can see that we can cancel out here, and then the magnitude of my magnet field, I can put everybody here outside, so it's going to be 0, 4 pi I over the radius, integral of d phi. Okay, so that means this integral here will be magnet field and 0, 4 pi, the current over r, and my angle phi. Agreed? So this will be my angle phi here. Okay? And one important thing, guys, this is really important, and I need you guys to remember this. This one here is always in radians. Don't forget that. It's radians, okay? Always in radians. So for this one, this specific case here, what's going to be my phi? Going to be pi, right? Because this is pi, right? It's just from one point to another one here. It's going to be pi. So my magnet field here will be magnet field will be 0 I 4 r. That means I just need to plug it in all the numbers. So it's going to be 4 pi times 10 minus 7 Tesla times meters per ampere, and this is going to be 34.8 times 10 minus 3 amperes, almost here. So divided by what? 4, 0.0926 meters. Okay, so after calculation, I just need to put here the number that I got and Tesla. Okay, so take a look. The magnitude of the field is 1.18 times 10 minus 7 Tesla. And this is for the letter A. Okay, so the answer for letter A is this one. Now, letter B will be, what is the direction? Well, the direction of this guy, it will be if we just use the right hand rule, shows that this field is into the page. If you do the right hand rule, it will be into the page. So this guy will be entering into the page here. Okay, so repeat this problem if you had some hard time here, and try to go over every single step. Of course, so I mean, we could use this answer already here because there is a formula supplied into the book about this one. But I I mean, I did everything here for you guys to see from where this formula comes from. Okay, so try to repeat this problem and try to figure out every single step here. Okay, so thank you. Let's do it.